The Harding Memorial Lecture this evening. As you know, it's the 25th anniversary of the opening of the Channel Tunnel, and BTS wanted to celebrate that, and by inviting a French tunneler across to give tonight's Harding Lecture, and also to give a clear message in these times of Brexit that BTS's doors are very much open. General de Gaulle has said, how can you govern a country which has 246 varieties of cheese? That's equally true for our country as well as France. So Bruno of Bouygues was going to come over and give today's talk. And as we all know, clients can be incredibly demanding, and contractors tend to jump when there's a tender in the offing. So Bruno has had to go out to Singapore on short notice. But Bruno's deputy, Thibaut Lockhart, has stepped into the breach. So this is a dual effort between Thibaut and Bruno tonight. But I'll introduce you first to Thibaut. Thibaut has been working for the Civils Works division of the French company Bouygues Construction since 2009, when he started as site engineer on the nuclear power plant at Fameville in Normandy. Since then, he has worked alternatively in Bouygues' in-house technical department in France and on construction sites abroad. In 2013, he was design coordinator for underground works on the Timelapse subsea tunnels project. Then in 2015, took his duty as engineering manager on the Idris Surge project in Doha, Qatar. More recently, he has been deeply involved in the engineering studies of the tunnelling works of High Speed 2 C1 contract. Thibaut has recently transferred to the UK branch of Bouygues Construction as business development manager. So I'll hand over to you, Thibaut, for a fantastic talk, I'm sure.
Yes, thank you very much for this very nice introduction. So I'm sure most of you know Bruno, who unfortunately couldn't come tonight. But I'm very glad to make this presentation on his behalf. We will try and give you a construction company's view on innovation in tunneling from our experience. The recent projects we've been involved with in the world, and try and explain to you what we foresee in the near future as key evolutions in the tunneling industry. A first slide, which is the corporate slide. The most important piece of information is probably on the top right corner. Is how do you pronounce Bouygues, so because we are getting asked the question many times and very often, so I thought we could clarify that. So it's Bouygues, and we are actually, I think I have the pointer here. We are actually the Civil Works division here, Civil Works division of Bouygues Construction, which has also some activities in buildings, and part of a larger group called Bouygues, involved in real estate, colas for the roads, media, and telecoms. Alors, the key messages for tonight. So, it's now commonly understood that robotics, the digital transformation, digitalization, as you heard sometimes, have and will strongly shape our industry. It's a great opportunity to increase the safety on our projects, because human beings will be taken away from risky places and replaced by robots where possible. More and more complex projects will become feasible thanks to the technology. And last but not least, tunneling in particular, and the construction industry in general, could be seen as a more attractive, maybe more high-tech activity, especially for the younger generations, thanks to the integration of all the new technologies. And tonight, the perspective I'd like to have throughout this entire presentation is how can we reach, as an ultimate goal, a tunnel boring machine. I will use TBM, but a tunnel boring machine fully operated from the surface that is able to optimize its production parameters on its own, autonomously, and react to simple events without the need for a human intervention every time something unexpected occurs. That would be the governing idea throughout this entire presentation. When I joined Bouygues in 2009 in Flamanville on the nuclear power plant, there was one robot on site. One robot doing use to grind the concrete walls and to remove to help the operators grind high walls. And it was like the robot. Everybody wanted to see the robot. It was the only thing that people remember from that site. Now, it can be seen that we have actually plenty of robots on site. It's becoming more and more common. So we will see the consequences of that evolution. We will start with a bit of history. First, very, very short, but to show you that there is a trend, a continuing trend up to now of mechanization and industrialization of this industry. Then we will go through three categories of innovations. First, you cannot innovate if you're not, if you don't have the complete mastery of your core business, your core area of knowledge, know-how, etc. So we will start by improving all the tools that we've got now. Then, that would be the second kind of innovation, we will try and innovate using other technologies that do exist already, but in other fields of the industry. A short break, we will go to Coombe, to Hong Kong, to see how we implemented that on the cross passages of the Coombe Cheklakop project. And then we will go to another kind of innovations, which are more like breakthroughs or game-changing innovations, which will start a new field of research, of experimentation, because they bring something radically different. And I will give a quick word on the big data, which is kind of a trendy word now, but from this perspective of autonomous TBM, what it means for us in this very specific context, because many people are working on the big data at the moment, and some perspectives at the end. Well, the concept of tunnel, of man-made tunnel, as opposed to caves or natural caves, is very, very, very old. But like many other fields of our industry, it has sped up in the past 2 centuries, since the Industrial Revolution and with the appearance of new techniques and new materials. So the shield and the boring machine appeared like 200 years ago, roughly, and the robots and the computer science, which are linked, let's say 50 years to 100 years ago. But now, everything starts to come together, and we will be able to, hopefully, to get the most of both worlds. If you look at the original shield, so this is the well-known image from Brunel, Sir Marquis-en-Bar Brunel's shield for the Thames Tunnel. And another attempt at a TBM that was originally designed to go through underneath the Mont Fréjus between France and Italy in the mid-1850s. you can see that our TBM today are not drastically different. The concept has not changed much because the problem is the same. You need to support the ground, you need to progress, excavate, install a lining or whatever you call it, walls, a roof, and stay safe inside. In the domain of robots, the evolution is a bit more recent, but the trend is the same. This, if you like Mechanised, it's a very, very interesting robot that was constructed quite a long time ago, actually, and it's the very first programmable robot that was designed to, using the same concept as the paper roll pianos with the paper rolls with the holes in them, designed to assemble bricks in a certain order and build a wall. We'll come back to that later in the presentation. And for computers, it's, again, a recent study has shown that the computing power, the raw computing power of the computers, I'm not talking about creativity or ability to learn, but I'm talking about computational power of the computer are somewhere between the mouse and us. So, above the mouse, that's good, but it's getting closer to us. And now, so it's a good time to try and ask ourselves how we can start working with the robots that will still be or are already as powerful as us, because we might be able to find a new way to share the tasks. In the 70s, we made an attempt with Bouygues to create our own TBMs. At the time, you couldn't buy TBMs everywhere like today. So you see, we had already the same concept as all the predecessors had. So try and have help the excavation with the mechanical parts. In this case, rotating cutterhead. It's for hard rock, so it's simple, but still. Some laser guiding system. It was the very, very first steps of what has become now the total stations and all the survey system that we've got nowadays. And we started tunneling, so it was in Syria in '77. Now, obviously, the scale has changed. This is Moon as well. The machines have become huge. You've all seen probably the S880 from Herrenknecht, and it's a twin. It's a TBM, so it's a sister who just completed their drives 5 months ago in Hong Kong. So the TBMs are much larger. They go much deeper in soft ground, and operating these machines has become more complex as a consequence. It's not anymore a guy sitting on an excavator. It's a real factory with all the equipments operated underground. And if we want to continue the evolution towards deeper tunnels, larger tunnels, more complex tunnels, and try and reach under urban areas as well with the control of the settlements, we will need to keep on improving our machines. So it's clear that our industry inherits from this very long tradition. So now the question is, how do we use or make the best use of the recent advances to make our TBMs better, or to help us with the operation of our TBMs? The first kind of innovation is the improvement of our existing tools. To streamline the construction of the tunnels, we've developed over the years many tools, but it's important to keep them up to date and so that they follow all the developments of the new techniques that appear continuously. You will see a software suite, Pixis, Gatsby, and Shiva, I will explain later, and our cutter discs with the instruments on them, Moby Dick. I will try not only to describe each and every tool like a catalog of all the innovations, I will try to explain to you why everything that we've developed over the past 30 years, 25 years, can now be integrated in this quest for the autonomous TBM. The guiding system, it's very important to be able, obviously, to guide the TBM because it's essentially blind when it's underground. So, what have we got? We have reference points at the surface and or in the shaft, in the break-in shaft at the beginning, and then we need to rely on laser pointers, laser targets to guide our TBM. The TBM is continuously moving, first because we intentionally make it move, but also because it has to react to the environment, to the ground. And sometimes it's pushed back by water pressure, it's pushed aside by a boulder, rock. You need to be able not only to steer it, but also to catch up with the theoretical alignment if the machine is not going where you would like it to go. So this Pixis system, over the past 25 years, has been designed to help the TBM crew decide where to put the key segment. What I call the key segment is when you have a universal ring design, you have standard segments and the key segment with a taper. And depending on the location of the key segment, you can turn left, right, go up or down, or a combination of everything. However, your theoretical profile that we would like to follow is not always followed actually by the TBM. So continuously you need to adjust. And what we've done recently as well, and what we call here the autopilot mode, is this system is able to act on the controls, the steering controls of the TBM, to react to a deviation with respect to the theoretical alignment in real time, without intervention or without constant intervention from a human operator. Of course, if it goes too far either side, it will ring and call someone. But like for small adjustments continuous during the excavation, when the machine is constantly moving and kind of vibrating, it will help. Then the amount of data that's collected on our machine is growing and growing, and hence we need a very, very strong data acquisition system. To give you an example, on a standard machine, slurry machine as we have now, for example, on the Grand Paris in France, you have more than 3,000 values per second that are collected by this system. By value, I mean it can be the rotation speed of the cutter head, it can be the pressure in the thrust jacks, it can be, for a slurry TBM, it can be the slurry pressure in the excavation chamber. For an EPB, for earth pressure balance TBM, it can be the weight of the muck on the conveyor belt, the parameter of the slurry treatment plant, many parameters that are recorded continuously, and it creates a huge amount of data, which leads to two challenges. First, we need to be able to visualize and analyze this data, and then we need to store it, and ideally to store it in a way that we are able afterwards to back analyze, so to analyze later on what happened during the site and use the experience of one site for the next one. This is the last bullet point here, the back analysis on structured data, so data in a standard format, stored always in the same manner for machine learning. We will come to that at the end of this presentation. more and more the clients, the engineers, the designers are working with platforms or interfaces that make it easier to control or just to know what happens on site. So this data acquisition system must be able to give also human-friendly outputs. Like for instance, where is your TBM? What are the main parameters that are used for the production? And generate as well reports, weekly reports, monthly reports at a certain frequency to know what is happening on site. Another example, you tell me why, but it's what happens during your shift. Alors, the shift, 8-hour shift, 10-hour shift, many things happen during the shift. And before, we asked the site engineer or the shift leader to write down after the end of the shift everything that happened in a notebook or on his computer, but it was written with his words. And not in a standard way, which made it very, very difficult afterwards to try and answer such questions, such as, for instance, what is the average duration of such task, or average at what time do the crew members stop for, I don't know, the pipe, the extension of the slurry pipes, etc., etc. Because everyone was using a different language, sometimes even. We decided now to use a tool that has a standard library of tasks for me to choose, and try and help as much as we can the people that just spend 10 hours in a tunnel to make it as simple as possible for them. Ideally, we want them just to have, with the voice recognition, just to, during their shift, to speak and say, okay, it's 10:35, I start this task. Or it's 10:47, I just finished that one. Okay? And it's all recorded. And it's recorded in such a way that afterwards, we're able to crawl through that data, to mine through the data, literally, and to use it for statistics, what we call chrono analysis. It's analyze the time that is spent per task, where is the waste of time, possible optimizations, etc. And identify patterns. Tasks that should go one after the other, but it never works for some reason. Tasks that should run in parallel, but it never happens, so you wonder why, etc. But what is very, very important here, and also in the view of the autonomous TBM, is that a TBM, a machine, as intelligent as it can be, will never be able to use this. It needs something more structured and more standardized. And lastly, for this section, the TBM is blind, as we said, or you have a class of technologies more using geophysics. I won't discuss that tonight. This is something else. It just literally fills the ground ahead of the TBM with instruments, so pressure sensors, temperature, rotation speed, force, etc., installed directly on the cutter disc, like inside the cutter disc. And doing so, you're able to know, for instance, in a soft ground matrix, if you've hit a boulder, because when the cutter head is rotating, your cutter disc will see the ground, and you will see non-linearity or a change, a steep change in a value, which after you need to explain. And since the cutter head is rotating 360 degrees, you end up by having a complete mapping of the tunnel face. In theory, it works well, and in practice, it works as well. We've used it also as a side effect. We realized that it's also a good way to know the condition of the cutter head. Because sometimes the value change not because the ground is changing, but because your cutter head or your cutter disc is worn or worn out or damaged. So it is also a good tool for maintenance. Here, for instance, on the project in Hong Kong, we expected to hit the bedrock at the tunnel invert, but you have boreholes every 200, 300 meters. You never know exactly where you will hit the bedrock. With a tool such as Moby Dick, you just literally see it, you feel it. Your cutter disc will feel it, and you will know not only that you have hit the bedrock, but you will know the level of the interface between rock and soft inside the tunnel, and you will be able, for example, to take measurements or to analyze more in depth this data. So far, it was just improvement of existing tools. It's a first step. It's a very, very important step because you cannot innovate until you're sure that what you do, you're doing it correctly. And what we've done here is not only improve our tools, is make our tools compatible or ready for the next step, which is autonomous machine. Now we will go on to a second class of innovations, which is sometimes the solution is not cannot be found in our own industry, and we need to look around and in the neighbor fields of engineering and try and find solutions from coming from others. I will take three examples of such innovations. Some of you may have seen, even for the first ones, some of you may have already seen these names before in other presentations, etc. I will try not to do again just a catalog of such tools, but just try to explain why now it will be integrated in a larger picture. Snake is a robotic arm designed to inspect and clean the cutter head. Roby is a multi-purpose robot coming from the car industry that we use for tedious or cumbersome tasks. Talia is our simulator that we have programmed to train our young pilots, TBM pilots. You'll see. So Snake, those of you who have been involved in or interested in the Port of Miami project in the US, what was like 10 years ago, 8 years ago, have probably already seen Snake. It was our first real attempt at such a robot. We took a robotic arm that's used in the aviation industry to inspect the tanks located in the wings of the airplanes with the camera. So actually, it just sees this is before the break-in, so you can see the head wall. It's remote controlled, and it can go inside the cutter head chamber and also through the holes of the cutter head into the ground. The purpose of this robot was to inspect, see, check, and you will see in a minute, clean the cutter disc. It's equipped with the water jets, so 8 bar pressure, to clean or unclog the cutter head. And it's fully remote controlled from the cabin, which means that you don't need to send anybody inside the chamber to do this work. A second example is Roby. Alors Roby, the video here has been made on the Liantang project in Hong Kong. We had many holes to drill to install brackets. Using robots to drill holes is not new at all. What we wanted to do here is use a robot as autonomous as possible, which means that we wanted Roby to do its own survey first to know where it is, where it was, then the drawings, the position of the dowels were input into the system. So he decided where to put the dowels. Drilling, obviously, that's the whole point of having a robot, with absolutely zero human intervention. It's drilling the hole, sucking away the dust as well, cleaning the hole, and install the dowel. Now, in terms of safety, it's obvious that we have removed a work at height situation. It's obvious that this task is not particularly motivating to do. The accuracy and the speed of the robot is comparable to or better than a human operator. The real breakthrough is that this robot never gets tired or never gets bored and just drills. We've done like more than 20,000 holes on Realtime. The robot has now moved to Australia in Sydney for North Connects, the highway project in Sydney. In a different context, because now you see it's SCL mining. It's a traditional excavation tunnel with a shotcrete lining, but the concept is the same. If you need to drill holes, you just need to know where the anchors have to be, to tell Robbie where it has to go, and after he will manage on its own. A more general remark, when you need to compare the productivity, it's not the productivity of the unit task. Drill a hole, it's a hole, it depends more on the drill bit than on the robot or the human being, or the operator. But as a whole, if you have a robot, you save time on everything else, means transition between shifts, lunchtime, dinner time, all the stops, etc. So overall, you go faster. The TBM simulator, again, this is an example of a partnership with a startup, a company specialized in simulation software. So car, planes, a lot of simulation software. And we've asked them to help us develop a TBM simulator with a realistic command panel. By realistic, we mean very, very close to the actual one that the pilots would have on a real TBM. Be able to simulate all kinds of tunnel boring machines, so earth pressure balance, slurry shield, slurry pressure, variable density. Using, and that was very, very important for us, realistic scenarios. So scenarios taken from our previous sites with the data collected by CATSB and all the tools that I've mentioned before, so that the training could be as realistic as possible. A young pilot, before he's sent, especially now that we have a significant number of tunneling projects and not so many experienced pilots, so we need to train new pilots. He will be able to get a first a feel on how the machine is behaving, how you react to a certain event, etc., before he actually goes on site to operate a TBM. Incidentally, you can notice as well that the machine can be entirely controlled or driven from the control cabin. The control cabin doesn't have to be necessarily on the TBM itself, underground. There have been some attempts to have, for large machine, I mean, for smaller machine, pipe jacking, directional drilling, etc., it's already the case. But for large machines, the Japanese, for instance, on the Tokyo road, have put a cabin on the surface, but it's a duplicate of the cabin that's on the TBM, like a double redundant system. But now we think that we can have the control cabin at ground level, even for a large machine. So you can see here the screens, as user-friendly as possible to display all the data simulated from past projects, and the pilots being trained by more experienced TBM operators or TBM managers even, so that they know how to drive. So what are we seeing here? Sometimes, so we've taken from the outer world, let's say, ideas that we try to implement on a tunneling job. There is nothing new, there is nothing groundbreaking in itself here. It's just that for a given problem, how do you find the solution that will best answer the question first, improve your safety, the safety conditions on site, productivity as well, and can be as autonomous, as industrialized as possible. And here, traditionally, the construction industry is a bit behind the other industries, so it's a good opportunity to catch up. Now, I would like to, as a short break, say to travel to Hong Kong and with you to have a look at the cross passages of Twin Moon. You've probably heard, it was published, and you've probably heard about the construction of these cross passages, because it's a good example of a situation where we didn't have any other choice than to innovate. And I will explain why in a minute. You have two tunnels, and what I call cross passage is the structure that connects both tunnels for emergency egress of pedestrians. It's a highway tunnel in case of fire or accident. Alors, the context, Twin Moon is a highway tunnel. You have two parallel tunnels from an extension of the Cheklapkok airport here to the new territories at the north here in Twin Moon. Okay. We had a significant number of cross passages because the tunnels are 5.8 kilometers long, and you had one emergency egress every 100 meters, which means 57 units, 57 cross passages. And the problems, as you will see in a minute, that the design that we had initially based our proposal on turned out not to be working. These are the two main tunnels with the carriageway, 2 lanes plus an emergency lane on the side, some equipment and ventilation underneath, ventilation at the tunnel crown, and cross passages. So you see, we had quite a significant number, and the geological conditions are quite challenging. It's typical of Hong Kong. You have the bedrock is granite, but on top above that, you have different layers of sediments, very soft, soft to very soft, highly permeable in this area, and up to 6.5 bars of water pressure below the sea. So two consequences. Below the sea means very, very limited access from the top. And second consequence, it's hopeless to pump. You know dewatering. So, sounds obvious, but... So why wasn't the initial concept working? The initial concept was based on artificial ground freezing, which has been done before, which is a known technique. But when we sent the samples to the lab after the additional ground investigation campaign, it turned out that the mechanical tests, so uniaxial compressive strength on the frozen ground, was much lower than expected. I'm sure Stéphane remembers this bad surprise that we had when we opened the factual report. Therefore, the dimensions of the ice ring around the cross passage, which is governed by the UCS of the frozen ground, was not feasible in practice because we couldn't even drill and install the freezing pipes at the bottom because we couldn't install the machine in the tunnel. And also, to freeze, you need time. And the larger the ice ring, the longer it takes. It was completely incompatible with the program. So we had to find something else. Now, I apologize for this slide. For the sake of completeness, I put all the constraints, so it's a lot of text. But we try to be quick. The constraints are water tightness against the 5.5 bar at the axis, so 6.5 at the invert. Ground stability in soft ground, that must be maintained at all times. Structural and design constraint that we have imposed on ourselves, not to create with our innovation something worse than the initial concept. We needed a structure that could spread the thrust loads of the main TBMs, prevent any ovalization of the ring, of the main tunnel. Ideally, we wanted the temporary structures to be part of or the permanent structure to avoid many operations of dismantling and reinstallation. And this is of paramount importance. We had to excavate the cross passages while the main tunnels were in operation, which means that we had to leave at all times half of the tunnel free for the logistic, for the vehicles feeding the large machines, the main machines. So you will see, naturally, we would have put like, I don't know, struts or props, like against the wall on the other side. It was not possible. It turned out that actually it was a good idea not to put them. I will explain why, but it was a significant constraint. And no support, no art trips, no ground treatment required because we didn't want to create with our innovation something worse than the ground freezing. Because if you replace ground freezing by jet grouting, you're back to square one, you haven't improved anything. So the new concept was, why couldn't we use the pipe jacking technique that is commonly used elsewhere, from shaft to shaft, for instance, but this time we could maybe use it from tunnel to tunnel. And the idea is to start from one side and push a pipe jacking machine, so a mini TBM, if you want, towards the other side, and retrieve it in a steel bell under pressure, because here you have people working and you're under atmospheric pressure and you're connected with the surface, connected to the surface. Here you're inside the ground, so you have your 5 bars of pressure on top in soft ground. What was the concept? So we had to provide a soft eye in the main tunnel lining. I will show that in the next slide, so that the pipe jacking machine can go through into the ground and on the other side as well. And then to prevent or minimize the ovalization of the main tunnel, we decided to cast a reinforced concrete frame inside the tunnel that would act both as a temporary support and frame for the pipe jacking machine, which was anchored to this frame through using 4 big steel plates to push the pipe jacking machine into the ground. And the permanent lining of the cross passages was the reinforced concrete pipes themselves. So we said, doing so, we use all the temporary structures to already create the permanent cross passage at the end. What was really challenging, I won't talk too long about that, but the waterproofing system, because you can imagine that it's a junction point, and traditionally junction points are complicated to handle in terms of waterproofing. The soft tie, again, nothing groundbreaking, because everybody is using steel fibers, not steel fiber, sorry, glass fiber reinforced polymer rebars to provide soft ties in D-walls, for instance. So we said, okay, we will use the same in segments. So we've chosen to design hybrid segments with a traditional carbon steel, black steel reinforcement, and GFRP rebars in the soft eye, and the soft eye itself had been designed so that for all possible orientations of the pipe jacking machine, going from one tunnel here towards the other on the other side, this is a plan view of the cross passage view from above. So you have tunnel number 1 here, tunnel number 2 on the other side. So this soft eye had to accommodate all the possible relative positions of both tunnels, plus the tolerance of the CP. And we've used couplers embedded in the segments to connect to the structural frame, because we want everything to work together. Therefore, we had all these couplers embedding in the segments and pointing towards the intrados, on which we've connected rebars here and cast the frame. Here you can see the frame with the big plates. You have 2 out of 4. The big plates to anchor the pipe jacking machine. The flange at the first part of the steel structure for the pipe jacking operations. And on the right-hand side, you see the cross passage completed. Here you can see the circle here is the trace of the pipe jacking machine. And we've just cast in situ the permanent opening, which is a door of 2.2 by 1.8 or 2.2 by 2 meters here for the pedestrians. And again, the temporary structure is the permanent structure. A few images, photographs taken during the site. Here you can see the pipe jacking machine arriving at its location. This is the jacking frame. All this was developed with the Herrenknecht, so they've helped us quite a lot to develop this concept. Everything is on trailers, so it can be moved from one cross passage to the following one inside the tunnel. The pipes, the concrete pipes, were brought using a flatbed truck, keeping at all times some space for the logistics. And the good thing with pipe jacking is that you have access to the tunnel, the cross passage, while it is being pushed or jacked. So we retrieved the TBM in the bell on the other side, which was pressurized because it arrived with the confinement pressure at 5 bars, etc., a bit above 5 bars. It had to go back, down to 0 here. So when the machine had arrived here, we ensured that all the waterproofing was installed properly and was working before we lowered the pressure in the bell. And when we opened, we could get the machine out and send it back to the next cross passage. 2 time-lapse videos that we show you. On the left-hand side, it's the break-in, launching side, and on the right-hand side, the break-out, the retrieval of the machine. Again, if you take all the pieces of the puzzle independently from each other, there is nothing here that is completely new intrinsically. But when you put everything together, you have a new solution. You have a solution that had never been done before. And this was typically the case of innovation under constraints because we had, again, no other choice than to do something else than what was previously anticipated. So the innovation was more in the process, the assembly of bits and pieces from other areas into one solution. It was made possible, now this is important, it was made possible through very sensible risk sharing with motivated client. The client was in the same boat somehow because the solution was not working, but he needed his project done. So we came with this solution that had never been done before. We had some risks, obviously, and we had to convince him that we could manage those risks, that everyone had to do his best to take his share of the effort. And that's one of the key reasons why we were successful in developing this process. As a result, we managed to do 42 cross passages with a production cycle, average production cycle of 20 days, which is much faster than the 4 or 5 months that ground freezing would have required, with a record at 14 days. And we will use this technique on a new project that was just awarded recently in Hong Kong as well, which is called Trunk Road T2. Very similar project with cross passages every 100 meters as well. We will go for this solution as well. We tried, for instance, we tried on HS2, but as you can imagine, this works in large enough a tunnel. You need large tunnels because to install all this equipment without interrupting the logistics, you need space. If the tunnel is small, or it's relative, but if it's too small, then you have to wait until you've completed your main tunnels before you do your cross passages. So the cross passages arrive on the critical path at the end, and it's not always a good idea. So now back to our autonomous TBM. Now we will go to disruptive innovations, like breakthroughs or innovations of a different kind, innovation that will open a new field of experimentation and research. We will start with the continuous boring. By that I mean a TBM that is able to excavate at the same time as it is installing segments. It has been attempted before. I will discuss that in a minute. And it's feasible in other type of machines, but I'm talking about large TBMs for soft ground and slurry or EPB TBMs. And two other, Telemac and a robotic arm to change the cutter discs without human interventions, and Atlas, this is the most recent one, the autonomous ring erection system. You will see that it has some similarities with the Meccano that we saw at the beginning. Continuous boring, it has been attempted before. The limiting factor for continuous boring was the level of control or the accuracy of the control of the hydraulic and oil systems for the thrust jacks and the computing time available on the machine. Because the main issue is that when you have your TBM in the ground, you will calculate the pressures in all your jacks so that it balances the forces coming from ahead, from the ground, from the water. if you, or when you want to install a new segment, you need to retract a pair of jacks, which means that this equilibrium is broken. It's kind of broken, and so your machine will move mechanically because the force that originally went into those two jacks cannot go anymore into those two jacks, which have been retracted. So it will redistribute around the n-2 other ones, but as a consequence, your machine will move. So we need to be able to control at all times and in real time what we call the center of thrust. Center of thrust is the barycenter of all the forces of the thrust jacks. I will show that in the next slide. And in terms of design, it means that if you continue, if you keep on excavating at the same time as your erecting segments, then we will have new dynamic effects on the segments for the design of the reinforced concrete. At the moment, when you design a ring, you, as an assumption, sometimes it's a hidden assumption, but still it's an assumption, you assume that the ring is formed before you push on it. The ring has been completely finished before you push on it. Now it's no longer true if we go for such a method. And it's made possible, and it's being developed with Herrenknecht on the HS2 project that we've got, the contract number named C1, number C1. It has become possible now because the computing time of the position of this center of thrust is now below a tenth of a second, where it was over 10 seconds 20 years ago. So now we can really speak about real time now. So we can do that. And what is at stake is, in real time, you have your center of thrust here. If it's on the bottom right-hand side, it means that I push more on the bottom right-hand side, so I want my TBM to go a bit to the top and a bit to the left. Okay? When I retract those two rams, I still want my center of thrust, the barycenter, at the same location, because I don't want my TBM suddenly to move in another direction, so I want to keep this, which means that I need to quickly calculate first the forces in the remaining jacks that are not retracted. But not only calculate, we need to ask the system to change the pressure, the oil pressure, the hydraulic pressure, very quickly in those jacks. So it's not only just the computing time, it's also the accurate control of the hydraulic system. We'll see when the machines on the two machines on HS2 start. It will be a very, very nice field of experimentation. What is at stake here is obviously to save time. To save time, because if you excavate, then you stop, you install your ring, you stop, you excavate. It's a natural idea to try and install and excavate at the same time. Second innovation is Timelapse, so a robot that will change cutter discs. The video here is the traditional way of changing cutter discs. So you take out the one that's worn out, you put a new one. Okay? That's the theory. In practice, it implies that you are working in the cutter head, so above 40, 45 degrees Celsius, humidity up to 100% sometimes, under pressure, under hyperbaric, it's a hyperbaric intervention, so 3, 4, 5 bars. You spend 2-3 hours changing one cutter disc. So when you have a full cutter head, so 80 to change, it takes a long time, even if you don't change them all at the same time, but still. So we say, okay, there might be a way, or there must be a way to propose something else. Especially now, we like to remove, again, all the operators from risky situation. And a cutter disc like that can weigh up to 200, 250 kilos. So it's really, really a hard, it's really hard work. What we've done, the robotic arm you've seen to drill the holes, we've taken the big brother, and we've developed something taking advantage of our machines being large that is housed in a compartment inside the shield, the front shield, the front part of the TBM, able to go through a door, access the cutter head from behind, take or grasp a cutter disc, and replace it by a new one. So in theory, it's easy. It has to work in hyperbaric conditions, to be remote controlled from the control cabin under atmospheric conditions, be ideally as fast as a human being, but if you manage to get all these safety improvements, you can tolerate that it's a little bit slower than a human operator, but the key improvements are no hyperbaric interventions, no people sent in the chamber, no work in confined space, and no handling of very heavy elements. This is the video of Telemac. This is in the factory during the commissioning, because in the real world you don't see really what happens, because to make the movie you would have to send ideally a person to make the movie, which is exactly what we try not to do. But you see the robot and all this study and this, the software, etc., takes advantage of all the latest technologies that we've got now. The BIM, the 3D modeling, the 3D models of the TBM, the cutter head, all the studies about kinematics and robotics, reverse kinematics. So you don't control your robot by telling him, go to the left, go to the right, go up, go down. You just tell him, go there. And he will calculate with the position of the cutter head, etc., the best trajectory to arrive at its final destination. So virtually, you're just telling the robot, change cutter disc number 87, and he will manage the rest. Or it will manage the rest. For that, we also had to develop a new cutter disc, because the cutter disc that I showed you in the previous video, suitable for manual handling, are not suitable for a robot. Therefore, we developed a cutter disc that is more complex, a bit more complicated, a bit heavier, but it's not a problem since it will be handled by a robot. And it turned out actually that these cutter discs are also stronger than the others, have all other advantages. And you can see here on the right-hand side, this is the robot, the Telemac, installing a brand new cutter disc in a housing, in a casing of the cutter head. And the last innovation for today, it's now, we've talked a lot about excavation, the tools, the cutter heads, etc. What about the segments? Because a significant amount of time is spent erecting the segments. This is a video from the 820 project in Hong Kong, which was completed in 2013. It was a standard erector, so remote control, with an operator here, who will just check that the segment is put in its correct position, check what we call gap, step, etc., orientation, and make sure that the lining is of good quality. What are not the issues, but the areas of improvement? We have operators close to the erector, which is a moving part, a very, very powerful moving part of the TBM, with all the hazards associated to it. Sometimes it's difficult to access the segments that you're trying to place, especially when it's at the invert. And also for the operator needs to follow the erector, so it needs to go up to install the segment at the crown, then it needs to go down to install the segment at the invert, etc. For a machine like Moon, which was like 14 meters in diameter, For each ring, the guy was traveling 200 meters up and down ladders or stairs for one ring. So it's good for the fitness, but still when you do it for 8 hours or 10 hours, it's a kind of a long travel. So we said, okay, there must be a way to improve that. The targets for Atlas were, in terms of safety, we wanted nobody close to the erector anymore. In terms of productivity, we don't want to lose time, obviously, so it has to be as fast as a human operator and as reliable. And in terms of quality, at least as accurate as a human. It might seem strange to have a robot not as accurate, but actually, for example, a step between two segments, it's very easy to feel it with your hand, actually. And the touch is very good at feeling very, very small difference. So a human operator is very good at the ring building because it's easy to correct the small effects. So we want a good quality. And we said, okay, if a machine is doing the ring building, then we would like, during the ring building, to do the as-built at the same time, not send surveyors the day after or 2 weeks after, etc., to survey the ring. Take advantage of it being a machine, very accurate, as you'll see, to do the as-built straight away, straight after the segment has been placed. The result is Atlas. At the moment, it has been installed on the EOL project, part of the Grand Paris in France. At the moment, like right now, it achieved 34 minutes per ring, so on average, 4 minutes and a half per segment, with a record at 3 minutes. A human operator is consistently between 32 and 36 minutes per ring. So it's as fast as an operator. At the moment, it's not yet as reliable, but the target is to save 1 minute per segment and have a real gain in speed. How does it work? Again, you have in 3D, you have your TBM, your segments, the theoretical position of your segments. You have everything you need in a digital format. You just need to give, in a way, eyes or senses to your TBM, to the erector. So we have a number of lasers. You will see a video on the next slide. Laser that actually see or look at the segments that comes from the back, that comes on the segment feeder, it's called, this conveyor. Then the erector grabs the segment and will put it in the desired location, because here, again, because you know the theoretical alignment, you know the position of your machine, so you know where you want to put the key segment, so you know where you want to put all your segments. So you just tell him, okay, segment number S1 goes position number 2, for instance. This is, on the left-hand side, this is the view from inside Atlas's mine, so it's the virtual representation of the tunnel that Atlas works with. On the right-hand side, this is Atlas actually working. You see the lasers and the sensors installed on the erector. We had to make a couple of adjustments on the design of the rings to make it suitable for Atlas. For instance, you will notice that we are no longer using segment bolts on our project. We've recently removed them from HS2 as well, from our project. We use dowels here, embedded in the segments. So once the segment is in place, they will stay forever, and they play exactly the same role as rock bolts, except that you don't need to send someone to bolt them and remove them at the end of the project, if required. So now we only have dowels, and also they act as centering pins to help Atlas install the segment at its location. This has been made possible also because with the TBM manufacturers, we have a good, we work together to integrate the machine in the 3D model, because obviously you don't want to hit the jacks or any other part of the TBM equipment with a heavy concrete segment. So for those of you who are interested, feel free to go and visit EOL or other projects. It will be a technique that will be tested all along the project there. This was for hardware, let's say, innovation in hardware, in tools, TBMs. What about the software now? A very quick word on the big data. We are collecting huge amount of data on our sites, as you know, and it's not only us. I mean, it's a general trend in the construction industry to have colossal amount of data. The thing is, now it's a very nice playground for all the new class of algorithms that have emerged in the past 5 years or so. Machine learning, you've probably heard such term of machine learning. Artificial intelligence is very broad, but the category of algorithm where you just feed the machine with raw data, but you don't guide the computer. You just tell him, try and find patterns, correlations, relationships between the variables on your own, and just tell me what you found afterwards. On the right-hand side, I will come back to that in a minute. We are developing a tool that we call the ground-machine interaction indicator that is precisely working with this paradigm, which is we give the algorithm all the collected data, and we ask the computer to classify, to sort them, and to try and find relationships between all these values. On EOL, for instance, we are collecting more than 7 gigabytes per day, which means that over a 3-4 year long project, we will have immense quantities of data. We have an infrastructure dedicated to the big data in partnership with Microsoft, with a dedicated computing platform, because this will not run on a typical desktop computer, obviously. What you want to do is you ask your computer, okay, try and find some pattern. Or sometimes it will find obvious relationships, such as, for instance, hey, I've seen that the force on the cutter head is equal to the pressure times the area. So you say, okay, good. But the thing is, it's an indication that it works, actually. Because this relationship is obvious to us, but it's not obvious for a computer that is kind of discovering everything. He won't have the mechanical engineering background to know that pressure times area equals the force. So sometimes it will also find tricky correlations which are coincidental, and then you need an expert in the field saying, okay, it looks like a correlation, but it's not. It's just a coincidence. So it's a very, very interesting field of research, and actually many people are at the moment are doing research on big data and data coming from tunnel projects. Here, what we've done is we fed our machine with all the parameters coming from the TBM, and we have asked it to try and correlate the behavior of the machine with the parameters of the ground. So we don't tell the machine this is clay, because clay doesn't mean anything. But he will kind of say, okay, if I get this combination of torque on the cutter head with this combination of pressures in the jacks, with I don't know, this temperature over there, and I don't know, like this reaction to the steering action, it means that I am in a material of class, I don't know, class 4, for instance, which reminds me of another project that Bouygues has constructed before, where we have operated the TBM in such a way. And what we try to achieve at the end is to have like a big database where, using all available data from past projects, we can ask a TBM on a new project, so in a priori unknown conditions, to assess what he or it has to do based on what he's learned on the back analysis of the past jobs, which is exactly what we want him to do when we want him to react autonomously to events. Okay, if in this class 4, I know by experience and by machine learning that if we push too hard, we will damage the cutter disc. And we want the TBM to adjust and to optimize the production parameters in real time based on everything he's been trained to do. Alors, so far, we've run on the Tune Moon, or three projects in Hong Kong, Tune Moon, 1128, and Liantang. We've run simulations. So what we've done is we've used 90% of the drive to teach, or for machine learning, to train the computer. And we've asked it, what would you do for the remaining 10%? We know what we've done because we finished the tunnels. But we've used those remaining 10% to test the algorithm. We have a 94% success. Our 94% success means that in 94% of the cases, on this remaining 10%, the machine was able to correctly define the ground it was in and correctly suggest production parameters. It's a suggestion, obviously, because like the tunnel was finished, but still, it's plus it will be improved and over and over again. The target now is to provide kind of an assistance to the pilot, suggestions to the pilot, who will remain the decider. But at the end, we want the TBM to be able to do that on its own. Few perspectives very quickly. You've understood. Huh? We want to reach the autonomous TBM. It's not yet. We are not yet there. We have the safety as motivation number 1, productivity as motivation number 2, obviously. We have the feeling that all the technologies are here and just waiting to be put together. The first results are promising. There is still a lot of work to do, and it's the price to pay for to keep our industry high tech. But what is at stake is very interesting. What is now required is a joint effort with all the tunneling community, clients, because we can do as a construction company we can do nothing without our clients because of the risks. Because it's innovation, so by definition, you have inherent risks coming with the innovation. And also an implication of the entire tunneling community from suppliers, supply chain, contractor, designer, everybody has to cooperate or work together to reach this end goal. So as a conclusion, I would say, in the years 2010, when I started, the robot was like the thing you had to see on site because it was extraordinary. Now we are more like here, so we have a combination of robots, machine learning, computers. We want to use that as a feedback to help the TBM crew. And the future might be, but like this is a hypothetical, that actually if we have robots doing what they do best, so tedious tasks, repetitive tasks, crunching massive amounts of data in real time, then we humans can focus on what we do best, which is added value activities. Thank you for your attention. I hope, I was too long. It was too long. Thank you for your attention. I don't know if you have questions or come back. Yeah, please. Other questions.
I think after that you'll be getting a massive influx of visitors to AO. So
I hope so,
be
yes.
prepared. So who's... can we have somebody on the microphones, please? We've got microphones. First question, then. Oh, at the back there. Name and allegiance, please.
David Kellett from GTE, Global Tunneling Expert. Thank you very much. Very good presentation, very thought-provoking for the future. If we were to go 2030 to Mars or wherever, what are your thoughts on how we would power these machines if you make them autonomous? Nuclear?
At the moment, actually, we are not limited by the power of our machine. To Mars, I don't know, but like for the projects we are doing at the moment, we are not limited by the power of our machines. We are more limited by the wear and tear of the components and the duration of the project. So before you, the largest machine, so the Hong Kong machine, which was 17.56 meters in diameter, was still powered by a substation installed in Tuen Mun by China Power, the equivalent in Hong Kong. So it's not yet the limiting factor. For all the data crunching, data mining, etc., it's not on site. I didn't say that explicitly, but all the architecture we've set up for the big data and the machine learning, etc., is actually installed by Microsoft in one of their server farms, as they call them, somewhere in France. And it's completely off-site. What we need, though, is a continuous connection between the site and the network. That's true. But in terms of power, I don't know if we will be limited first by the power.
We have another question. There we go. So your name and allegiance, please.
Hello. Yeah, I'm Asal from University of Warwick in the tunneling underground course. My question is regarding Atlas. Now, generally at site we face some difficult situations while ring building, and we have to do many ad hoc improvisations. Suppose if the TBM is at a difficult angle, then is Atlas capable of that? That it does those improvisations and it builds rings in such a way during a tight curve or some difficult angle that they don't crack?
Well, this is a very good question indeed, because first, the notion of improvisation for a computer is slightly different, because by definition, for a computer, either he knows how to do it or he doesn't. Often we have to improvise on our sites because we are out of the usual ranges for value for. So we need to come back to a more correct, let's say, alignment, or correct the plane of the ring, etc. Atlas is not capable of improvisations in the same as you would say for a human being. The purpose of Atlas is not to arrive in a situation where you would have to improvise, actually. And the purpose of Atlas, if it's working properly, is to be able at all times to control the ring building so that you don't have to improvise, so that the quality of your rings is correct. And that's the second very important point, and the computer shall know where to stop. And at last shall be able to call for assistance or call for a human, for the TBM crew, where the situation is out of the range, of the operating range for which it has been programmed. Okay. So short answer is no, it will not improvise. And slightly longer answer, it's the whole purpose of it is not having to improvise anymore.
So how far ahead can it predict that it's going to crack? So I stop and I call for assistance. Like how far rings ahead?
Alors, EOL, at the moment, they have done a couple hundred rings, so it's a start. It's a start. We will have a feedback. Obviously, we haven't. It's a very recent one. This innovation. We haven't a feedback over 10, 20 kilometers yet. It will come. At the moment, it's still experimental.
Thank you.
Another question.
Hi, Christoph Euler, McDonald. Thibault, you said that there is an aspiration to bring designers into this overall context. How will you define the interfaces to access your, basically, this big software package? Is there some sort of standardization effort ongoing for that?
It's a good question as well. The first attempt at standardization was made between us construction company, and the TBM manufacturers, because obviously we had to speak the same language in order for our software to run on their machines. For the designers, at the moment, for instance, on Twin Moon, the lead designer was Arup. We had to collaborate with them very tightly, because the design of the pipe jacking machine, the design of the cross passages, etc., was shared between our in-house technical department within Bouygues and Arup. So it was not about the software, then it was more about the object. When we want to innovate, we have to take the designers with us. If now you're talking about all the data that's collected on site, also you have all the results from the instrumentation monitoring that's at ground level, sensors, settlement sensors, inclinometers, etc., which are continuously fed into the system as well. You have a few standards that exist already, but outside the construction industry, that link to transmission of data, how you format the data so that it can be sent through a network. This has been done already. After, by experience, what is harder to standardize is the definition of the data itself. For instance, I said you have 3,000 values per second on a TBM, typically, but actually, 1 second is already the result of an average of all the readings every 30 milliseconds. So after, what do you take? You take the average, you take the 5% fractile, 95% standard deviation, average. So all this is discussed at the moment on a case-by-case basis, and there is no standard.
Hello, thank you very much for this interesting presentation. Thomas Constantis from Mars. I have a question about the autonomous TBMs and the big data. You showed an example from a test to the machine, I think in Hong Kong, and you had 94% of success. If we are to use this in a way tomorrow, what would be the acceptable failure percentage in terms of risk and the consequence of a failure without any human intervention? Thank you.
That's the question when you want to delegate a task to a robot, and not only for this one, but for all of them, is as a general rule, you don't want your robot to do or to perform worse than a human operator, as a general rule. So for this 95%, it has to be maybe more accurate. 84% was the percentage of success with which the system correctly guessed or deduced, inferred the geological conditions and the production parameters. It doesn't mean that in the remaining 6% it was completely off target. And actually it was not far. The thing is, even with the human pilots, not two pilots have the same way. It's also a big difficulty in what we are doing. Not two pilots drive a TBM in the same way, the way that not two people will drive their cars in the same way to get from point A to point B. So one pilot will rotate the cutter head more slowly but push harder with the thrust jacks. Another pilot might want to rotate the cutter head faster and push and be a little softer on the segments. There is no real truth, though it's hard to say if the machine is right or not. What we want to ensure that whatever the automat does will not be worse than what a human being would have done. Okay? So, to answer your question, what we've done is this automat is also installed on the Grand Paris. It's not yet in control of the TBM, but it's trying to guess what the pilot should do or could do. Okay? We will see. We are constantly monitoring the suggestion from the machine compared with what the pilots are doing. What we want to define after is like thresholds beyond which the machine cannot go. And thresholds, if you reach them, you need to call a human being at the moment.
Any more questions? Okay. I think one more hearty cheer for a fantastic Harding lecture, please. Could have the slides for the chair now. Health and safety course in 25th and 26th of November. We're down on numbers this year. We've 34 attendees at the moment. We normally target about 60, and we normally get 60. For some reason, we're not getting it this year, so perhaps if you could go back to your host companies and push this. It's tremendous value, £150 for members. It's a 2-day course and that includes food, and £190 for non-members. So there's something to put in your diary and get people on that course. Next, please. Our Christmas meeting will be a real Tideway jamboree. Young engineers to talk about what they're doing on Tideway. Andy Alder, who you all know, is arranging 4 speakers to come along, talk about Albert Embankment, Blackfriars, Putney, and the TBMs. For those of you who are not involved in Tideway, this will be a good opportunity to look behind the hoardings and find out what's happening now. Next, please. And there's some indication of what is actually happening behind the hoardings. Next, please. And then looking further forward into the new year, Thursday, our first meeting in the new year, Thursday the 16th of January, tunnels in Norway, technical challenges, and the speaker, I'm hoping I'll learn how to pronounce that before he comes here, but I guess it's Ton Nokstad. Next, please. Something very important. I hope most of you will know that the May bank holiday has been moved to mark the 75th anniversary of victory in Europe, which has meant that we've had to move our dinner to the 1st of May 2020. This is not, I know normally it is the bank holiday weekend, but it's not the bank holiday in this case. So make sure to put that date in your diary. And if you've booked your holidays around that date, I need to remind you that isn't the bank holiday. Next, please. Again, our book, it's moving forward. We're really looking for writers of stories at the moment. I think it's fair to say we've been inundated with offers of stories, but we need people to put pen to paper or finger to laptop. People to see: John Corcoran, John's around somewhere, John's here, and Ken Spivey. Next, please. And tonight I'd like to thank our two sponsors, Sika, who will be, Sarah will be emphasising her French connection because Sika are sponsoring sausage and chips, and Bouygues are sponsoring the bar. Next, please. I'm growing used to this. I've got to think of an excuse to put it up. Two things, or three things actually. We'd like to possibly welcome is the wrong word because you were a little bit late, Alan, but we'd like to welcome all of the MSc students here tonight. Thank you for coming along, and I hope you've enjoyed the talk. We'd also like to advertise our blog, that we're looking for comments on the tunnelling specification before we update it. What I will be doing in the next few days is sending around an email to all members and all corporate members, providing a link to our blog website. And finally, as most of you will know, BS 6164, the new edition, is now published and is available. Other than that, please, when you get your beer tonight, go in and get your sausage and chips as well. There's now a tremendous atmosphere in both rooms, so please make the most of it. And the bar is open. Thank you.